All right, class, is your desk cleared off?
Oh, yes.
Are you ready for math?
Are you wrong? Yes. Waterfall, guys. Everyone, silent waterfall.
Alright, well, good morning. I think we've all had a great start to our morning. I love seeing how your brains woke up, working on that. It's not a far drive. Alright, so today we're gonna jump into math. You will need your math workbook, but you don't need to open it up quite yet. You'll also need a pencil. And we're gonna continue building on what we learned yesterday. How can we find the value of a 2-digit times a 2-digit multiplication expression using the partial product algorithm? So yesterday we did, I think, a 2-digit, 3-digit, 4-digit, and we just multiplied it by a single-digit number. So today we're gonna do a 2-digit times 2-digit. And why are we doing that? Well, because this helps us solve multiplication problems efficiently, and it helps prepare us to use that standard multiplication algorithm that you'll get to use in the future. And you said that's in 5th grade. So you're gonna get some of the steps you need today to start thinking about that. And then your success statements today, hopefully by the end of today's lesson, you'll be able to say, I can break apart 2-digit numbers by place value. I think you guys will rock that. You've already been doing that. I can find all the partial products. I can add the partial products to find the total. And I can explain how I found the products of the original expression. So take a moment and look at this. We're gonna just focus on this first one before we talk about the others. 30 times 7. Take a moment, do that mentally in your head, and chat with each other. What did you guys do for that? Just did it real quick in chat. Alright, class, what do you think? What is 30 times 7? Mal, what do you think?
210.
210. Do we all agree with that? Yep. Okay, now, 15 times 14. And if you want to look at this, we are on page 137. Since we're doing these mentally, you don't need to be in your book quite yet. But if you'd like to see it right in front of you, you can open your book to page 137. Before we solve this second one, I want you to really look very carefully and see how the factors in the second problem are related to the factors in the first one. Are you noticing anything? Because again, we're just doing this mentally. But how are these factors in 15 times 14 related to 13 times 7? Go ahead and turn and talk for a moment.
It's just importance. The 2 and 10 is importance. She's not.
All right, guys, what are y'all noticing about 15 times 14? Bowen, what do you notice?
That they split the 30 in half and split the double the 7 into 14.
Yeah, I noticed that too. So 15 is half of 30, and 14 is 7 doubled. So guess what? This is actually a strategy that we can use to mentally solve problems that we might not know right off the top of our head. 15 times 14, that one's a little tricky just to solve mentally. So if we, this strategy is called doubling and halving. And so in this situation, they halved first and then they doubled. But you could, if you wanted to do this one, you could think of it in this way. So if you take 15 and you were to double it, and then you were to take 14 and have it, I wonder if 15 times 14, what would that equal? Guys, we'll take a second and chat about it. Are you thinking about it differently now? What are you guys thinking? Are you making sure you're doing all four of the represents four digits, we have to have four equations if you're breaking it apart that way. And 120. Alright, what are y'all thinking about this one? What are some of our answers for 15 times 14? You guys noticed a connection there. You noticed that 15 is half of 30, and you guys noticed that 14 is 7 doubled. What are you guys thinking the answer is to this one? What do you think, Nora?
210 because you're just decreasing 30 and increasing 7. So they're technically like related. And I gave me a hint, like those are related. So like I knew they'd have to be somehow like the same.
Yeah. Did you work it out with an area model or the expressions just to double check, or did you just notice like if I? Well, yeah. How did you get that?
So first I was I had Lala and Ivy helping.
Yeah. No, I love that. I wanted you guys to do that. That's great. So you guys just noticed the connection there. That. Oh, do you wanna add on to it?
I just knew that. I just knew that if I don't know how to say it.
Yeah, no, that's fine. Well, this is a strategy I don't think we've talked about before. So what are you thinking, Turner?
The first time I did 10 times 10.
Okay.
I got 100.
Okay.
And then I did 5 times 4, I got 20, so I thought it was 20.
Oh, so you did 10 times 10 because you wanted to account for this group of 10s here and this group of 10s here. So you got 100. Okay, and then what did you do next?
And then I did 5 times 4.
Oh, you multiplied your 1, so 5 times 4. And that got you 20. And then you just said, whoop, I'm good to go.
Yeah, and then I realized that I wasn't, and then I did the same thing.
So then you realize, because when we're multiplying two-digit numbers, if we were to write out all the expressions or all the equations in expanded form, we would also need to make sure that this group of 5 ones was multiplied by that 10. So you would also have 5 times 10, and then you would also have, what's the other one I'm missing? 4 times 10. Because I think, Sloan, I saw that you went ahead and did an area model to check.
Yeah.
And if we do all the math out, we get 210. But just a really quick way, if you ever come across a number like this, like an expression like this, 15 times 14, and you're like, ooh, I really want to do that quick. There's one of the strategies is turn it into something you are familiar with that can be friendly. So then you can take 15 and double it, turn it into 30. You can take 14 and halve it, which makes it 7. And you guys are awesome at doing mental math with a 30 times 7. So let's try this one here, 50 times 8. Take a second. What is that one? You guys are welcome to chat with each other. 400, okay. Are you noticing anything about what we just chatted about that might help you with 25 times 16? What do you get if you do out that one? What do you think, Piper?
You would get 400 for 50 times 8 and 25 times 16.
Oh, and you know that because?
50 divided by 2 is 25. And 8 times 2 is 16.
That's right, because we took that 50, because we can look at these and see that these two numbers are related, these two factors are related. If you were to double this and then do the opposite thing, if you were to have this the 50 into 25 and you were to double this, we get this equation. But if you go backwards and you double the 25 and turn it into 50 and you take that 16 and you have it, so you're doing the opposite thing on both sides, you turn that into 8 and you can very easily do that mentally. So really quick, if I give you 12 times 15, is there something that you can do with that strategy, that doubling and halving strategy? Take a second, think about it. And then which factor would it be helpful for us to double? And which one would we have? Go ahead, you guys can chat about it with your table group. Which one of those would you double? Which would you have? What would make it really friendly for you to do mentally? That's okay. So it's just this, if you see how this one is, if you were to go backwards, we don't really know the answer to this one, but if we do double this side and get 3, and we halve this side and get 7, so since we're doing opposite functions on each side, again, these will end up being the same. So that one right now is kind of set up similar to this one. That 12 times 15 is similar to this. So how can we use that doubling and halving strategy? Which one of those digits could you double? Which one of those could you have to make it really friendly for you to just quickly figure out? What do y'all think? What should I do to that 12? Should we double that 12? Should we have that 12? We want to do it mentally really quick. What do you think, Lane? We'll have that 12, and now we're going to do the opposite thing to the other side. So what would our 15 do? If we double the 15, what would that give us? 30. Okay, and then if we multiply that together mentally, what do we get? That's a lot friendlier. Owen? 180. And I assure you, if you took the time to do an area model or write out all the expressions, you'd end up getting 180 too, just because of that relation there. All right, so we're gonna move on. This is your cool down from yesterday, and I just want to show you guys one thing I noticed so we can chat about it. I saw a lot of people trying our new to us, the partial product algorithm. So we did a great job of setting it up. 1023, and then we were multiplying by 5, so we did this. Then we went through and we said, okay, 5 times 3, that's 15. We did a really great job of keeping our place values lined up. Okay, then we said 5 times 2. Oh, nope. 5 times 20. I think we said that was 100. Whoops. Then we had 5 times 0. Okay, 5, and then 5 times 1,000. That's gonna be 5,000. Right, gonna add them all up. Got 10 going on here. 2, 1, 5,120. I see lots of hands. You guys don't agree with what I did there?
No.
You guys aren't agreeing with that? Why not? You take a second and chat. What did you guys notice when I see a bunch of hands? Why are you guys not agreeing with what I did?
Plus, they can put that at 500 plus 10 times.
You think that? Thinking about it. Alright, class, where did I go wrong? What did I do here? What did you guys notice? Ivy, what do you think?
When you did the 5 times the 0, it's not 5, it would always be 0.
Why? Because I saw a lot of kids do a 5. I saw a few kids do 50. I saw somebody even try out a 500 because they wanted to honor that place value. Why are you saying I have to do a 0?
Because when you times it, it's not really like, it's not a 1, like it'll be 5. It's a 0, so it would be 0. Anything times 0 is 0.
Anything times 0 is always going to be 0. So I think that just tricked us for a moment because we were really wanting to honor the fact that we were doing something. So we jotted down something. So just keep that in mind. This needed to be 0 to get the accurate answer. But I feel like you guys did a great job at working through that cool down. You showed me your reasoning and I loved it. So, all right, now take a moment. Let's look at this one. 64 times 87. Use whatever strategy you want to use to solve this. We are on page. Actually, we're not on a page. There is a page? Oh, yeah, I didn't want you to look at that page yet. So, at the bottom of page 137, where we just kind of, oh, you guys get to see all my notes. At the bottom of page 137 on those that warm-up page, go ahead and just work this out however you're most comfortable. How would you do that? We've got a few different strategies that we know how to use. How would you figure that one out? Question for you. As you worked through that, if you used an area model, show me a thumbs up. If you wrote out all the equations, show me a high five. Still seeing some thumbs up there. All right, so real quick, let's fly through this area model. So what number would I put here? You guys can just shout it out for me. 60. So we're gonna decompose 64. So then what would I put here? 4. Let's decompose 87. What would I put here? And then that would leave this in our ones. So if I go through this real quick, you to see if you guys got the same thing. Whoa. Let's have that stay right here for a second. 420. So I've got all these partial products. Did you guys get the same thing in yours? Did you add up all your partial products? What did you get? Let's see. We come up here. This is still just another way of thinking about it. It's still the exact same thing. Alright, double check my answer. Is that what you all got? Same several, same Sloan, Bowen, Henry, Herbert. Okay, so yesterday we talked about that. Did anybody try that algorithm from yesterday even though we didn't do a 2 digits? Ooh, you did. Anybody else? You did too, Sloan? You broke it apart with all the things on the bottom? You did too? Oh, let's see. Okay, well, let's talk about it. Look at this. Tyler also tried to use that algorithm that we used yesterday, the partial product algorithm. Take a second to look at it. See how the numbers we just talked about on that area model and on the expressions, they're the same thing that's going on here. It's just a little different because now we're doing 2-digit numbers. Another way so when we look at this, look at what you just did with your area model. I think most of you said that. How is this similar to that? Are you seeing the components, the same components in there? What do you think, Bowen?
It's similar because they did the same thing. And like they wrote their answers out in a row.
They kept all of
Because
this.
they did, first they did 7 times 4, then they did 7 times 60, then they did 8 times 4, and then they did 8 times 80 times 60.
And they got that. Here's another way of looking at it so that all of us can kind of visualize it the way that works for us. This is the same, this is all solving that same problem of 87 times 64. It's just 3 different ways of thinking about it. So today, this is what we're going to be working on, is the not standard algorithm, the partial product algorithm. Let's see. So what do you guys notice about how these are all related? If you think back to our lesson yesterday and how the colors all work together, how does this all work together and which one do you like best? So far. What do you think, Big Mouth?
Well, I like the one on the very far right because that one.
This one here?
Yeah.
Yeah.
It helps me like to not get them all mixed up.
Oh, so you like this one because it kind of helps you just very clearly see what's happening. Do you guys remember the other day when we were doing 2-digit times 2-digit multiplication and it had an area model that looked like that? We also discussed that because we have 4 digits, we must have 4 equations. So this way does really help us keep that organized. So let's see about this one. Can you find the value of 31 times 15 on your own? Let's do the method that Tyler did. I think Piper and Ivy and Sloan, I think you guys shared that you did the same thing that Tyler did. Let's try that partial product algorithm. And then go ahead and draw an area model to see if your answers agree with both methods, if you get the same thing. Yes, oh yep, and you can work this out on page 138. That second half of the page is a bunch of space for you to work on that. You'll notice at the top of that page, there's a different problem that's following the same format that you can refer to. Very close. Think about your place value when you're doing it. So you multiplied 5 times 30 for this one, and 5 times 30 give you this. Yeah, and then check it. I think you need to check at least one more of yours. Oh, so we gotta go through it each time. So we have to, 5 has to have a turn with each of these numbers up here. So you were right, 5 times 1. And then 5 times 30. So if you think about it, you could, if it's easier to think about it, there you go. Now, 1 has to take a turn. 1, or this is, but is this really a 1? Place value 7. Yeah, so 10 times 1. And then 1 times 30. Yeah, you got it. So then you would write that. Yeah, then you'd add all of those up together. It dies, yeah, because that 1 is in the 10 place value, so this is 10 times 1. Well, if you take 10 times 1. So with this one, I'm gonna have Piper write the partial product algorithm up there, and then, let me see. Would you mind And then Harper did the same partial product algorithm, but then he did an area model to check his answer. So let's take a look at what they're doing, and you can check your own paper and see what you think about it. right, what are you guys thinking about what's going on up here? It looks like Harper and Piper got the same answer. Oh yeah, you agree? Oh, you're telling me the same? Let's see, so they did 5 times 1 is 5. Oh, and Piper, thank you for writing out the expression there. So 5 times 1 is 5. Then we have to still make sure that 5 takes a turn with each of the digits above it. So 5 times 30, because is it 5 times 3 or 5 times 30? That's right, because this 3 is in the tens place. So this is really 5 times 30. So that's 150, which Piper showed us here. And wrote the expression as well. And then we can't forget about this lovely 1. Is that a 1? Right here in front of the 15, I see a 1. What is that?
It's a 10.
That's a 10 because it's in the 10th place value. So 10 times 1 is 10. And then 10 times 30. What's that? 300. Yep. And then if you add all these partial products up together, you get the answer, which is the final product, is 465. And then Harper, he's got the same thing going on here. He decomposed 31 and 15. He did all the multiplication right here, got all his partial products, added them up, and got 465. All right. So let's look at, before we jump to our cool down, let's take a look at this one for just a moment. Can you spot the error in Han's computation? You guys can turn and talk with one another. You can work it out in your book. We are on page 139, kind of in the middle. Do you notice an error? If you were to work this out, do all the multiplication step by step, what do you think? Are you noticing where you went wrong? No, you're doing great. You could also just think about if we're thinking about those place values, you guys helped talk me through it on the last one. There are a couple times I was like, oh, let's multiply by 1. You guys are like, it's a 10. What are you thinking over here? What's 7? Let's see, 7 times 1. Do you agree with that? What about 7 times, now what number is this? What's the place value?
50.
Okay, so with 7 times 50. You what? Yeah, is he? He thought he was multiplying by 5. So make sure that, what's 7 times 5?
35.
Oh, I mean 7 times 50 though. So make sure that with your place values, you wanna make sure those are lined up. Do you guys see another error? Where you have the wrong with it? Alright, what are y'all noticing about what's going on here? He had the right idea. I'm really impressed. He remembered to line up his 10 or his 1s, and he lined up his 10 so he could keep it very organized. But where did you guys find an error? Henry, what did you notice?
He did 7 times 5 instead of 7 times 50.
Oh, right here. And why is it not 7 times 5?
Because the 5 is in a tens place and that means it's 50.
Oh, so what did this need to be?
350.
350. So So this is really supposed to be this, and this is really supposed to look like that. Do you guys notice one more error? Harper, what did you notice?
One's 200, but he still did 5 times 40, so we need to add a 0 on the 5.
So this one here, you're saying, oh, he's really struggling with thinking about that 5. He keeps thinking that's a 5 and he's forgetting this is really a 50. So this should be 2,000. So then once he added up all his partial products, and then you'd be able to get the right answer. All right, so we're gonna go ahead and look at today. So you guys got to learn about multiplying two-digit numbers with partial product algorithm to find another way to think about multiplication, make it organized, make it efficient. So I'm hoping when you take your flow down, hopefully you can say, I can break apart two-digit numbers by place value. You guys feeling success in that? Yes or no? Yes, yeah. Success? Some of you are like, not yet.
Actually, meh.
Meh? Well, I appreciate the honesty because we're still starting on this unit, so we'll keep working on it. How about I can find all the partial products? Feeling pretty good about it? Success? Like, no. Add the partial products to find the total. I think y'all are pretty good at just the basic adding all of those together. Are you able to show how you got what you did? Are you able to explain how you found the product of the original expression? What do you think? So, I think some of our common classes are gonna line up. So we have, find the value of 15 times 43. It does say just show your reasoning. So that means however you are most comfortable solving this, you can do that. Once you're done, turn in your paper and then quietly line up in case anybody's still sitting here. So we can go on to our switches, okay?
Thirsty. Today's Friday. What? I did. In the bag. I want to say this. Here's your radio.
If you've not done so already, go ahead and make sure your name's at the top of your paper.